Yay, we did it even without our meeting host. So we have a pretty good audience online. Okay, well, thank all of you for joining us today for Benoit's talk. This is Benoît Epinat. He's coming to us from CFH, and then before that from Marseille, and before that from Paris, I think.
Yeah, my studies, yeah.
Yeah, master's study. So Benoit got his master's, actually got two masters in astronomy and astrophysics in Paris, and then photonics and optics in Paris.
You know that?
I do know that. I know some things about you. And then he got his PhD under Philippe Amram in Marseille. Took a small sojourn to Toulouse to work on the massive samples. So these are Redshift 1-ish galaxies
exactly.
with Symphony on VLT. And he was there for a couple of years working with Thierry Contini, right? And then he came back to Marseille, where he has been since 2011 affiliated. That's actually when I started at Marseille. So we came at the same exact time. He came on a unicycle. I came by metro, I think.
I took also the metro.
Did you? Okay. You did unicycle all the way through.
Just a small part.
And since then, he's been advisor to many, many students, including one in this room. And since about 2.5 years, you've been at CFH, where he's the instrument scientist for CITEL, which is an IFU, and also for WIRCAM, right?
I started with WIRCAM, and then I moved to CITEL last year.
Yeah, so Mauna Kea observatories, VLT, synergy of all these, and Benoit's going to talk, I think, mostly about your VLT work with Muse, the GTO time with Muse, and the magic samples. So please, Benoit.
Yeah, thank you for the introduction. Very complete. Okay, so first, thank you for inviting me to do this talk, first of all. This is a work, a project on which I've been working for lots of time. As you can see here, this picture here is from 2017. So it was already 7 years ago, and the project started before that. And I spent lots of time on that. And so what I will present is the project in general. So we had the project, the survey paper published very recently, but we also have other results that were done before that. It's a bit of the contrary side and reverse as we would expect. And so this project was done with Thierry Contini, which was the PI of the project. So we were both really on that project together. And here I also mentioned two students that worked really on the core of the project. Wilfried Mercier and Valentina Abril-Gaprero. And also I want to thank the Muse GTO team that enables us to do this very nice project. So as you can see here on this picture, the project is about looking at, the project is called MAGIC, which stands for Muse Galaxy Groups in Cosmos. So as the title says, the idea is to look at groups of galaxies. As we can see here, it's at intermediate redshift. It's not really local universe. Because we think that in groups and in dense environments in general happens lots of things that makes galaxy evolve probably faster than in low density environments. So really the goal is to probe the role of environments on the galaxy mass assembly. So the outline of my talk will be to start by introducing a bit the galaxy evolution and also the impact of environment on this evolution. Then I will describe the MAGIC survey, which is then the paper that have been just published. I will then show the results about the impact of environment on scaling relations, which was really the core of the project. We said the main idea when we did that. And then I will show you some nice results that were not expected, some serendipitous discovery of extended nebula in dense environments. And then I will make my conclusions talking about the future also about this kind of topics. So to start with, really general stuff. So when we look at the galaxies in the local universe, we clearly see a dichotomy between red and passive galaxies that are elliptical shapes on the one hand, and on the other hand, you have the star-forming galaxies that are mostly spiral galaxies that are gas-rich. And And so this clear dichotomy, so we have the red sequence and the star forming sequence. If we look back in time in the universe, we see that galaxies are really different. And this Hubble sequence we see in the local universe is the result of the evolution of galaxies from the early times. And when you go to early times, you see that galaxies are more clumpy, they are more star forming, they are smaller in size for a given mass. And smaller and smaller, you evolved this galaxy into this Hubble sequence, and in particular, you build up the red sequence of galaxies, so these dead quiescent galaxies, elliptical. This is another way of looking galaxies, looking their properties. So here in this plot, you have the star formation rate as a function of the stellar mass, and if you put all the galaxies you see in the universe there, you will be able first to draw a very nice sequence of star-forming galaxies with a linear relation between with a linear in log, but between star formation rate and stellar mass. So these are the main sequence galaxies, and the red sequence galaxies are mostly massive galaxies, but not only, but there are many here at the bottom of this graph with a very low star formation. And when you look back into redshift, what you see is that for a given mass, this star forming sequence of star forming galaxies, this main sequence, is going up, which means that the galaxies were more star forming at a given mass at earlier times. And this coincides with what we see when we look at the cosmic star formation density that we have that peaks between redshift 1 and 3. So we want to understand what makes the build of this red sequence. And one way to look at that is to look, I mean, there are several possibilities to that. And this nice work that was done here in the local universe on SDSS by Peng et al. Shows very interesting things. So the idea is that they are looking, so what we show here, the color code is about galaxies being, is the fraction of quiescent galaxies that you have as a function of the mass and the environment. And what we see is that if we look the fraction of these galaxies, when you fix the environment and you go to higher mass, we see that we have more quiescent galaxies, which is what we see basically in this graph on the right. But the other thing is that even at low mass, if you go to denser environment, we see that the fraction of quiescent galaxy is also increasing, which means that there are two modes of quenching star formation. There is the mass quenching and the environmental quenching modes. The environment has other impact on galaxy. One important result is that it seems that galaxies in dense environments have a contraction of their baryons, meaning that their size are smaller for a given mass. So this is a result based on subclusters with a comparison sample from the 3D HST that shows that we have a difference in size between those two classes of galaxies. So I mean, when I say we, the astronomers try to find ideas what can be the reason, the mechanism, the physical mechanisms that produce these changes. So basically, we think about two main classes of mechanisms. The first are the hydrodynamical mechanisms, so it's interaction of gas, and the most probably the most important one is what we call the ram pressure stripping. So ram pressure stripping occurs when you have a galaxy that moves fast into a dense environment. So what happens is that when you have a cluster, for instance, you have hot gas inside the clusters. And when the galaxy is typically spiral and gaseous, I mean, with a large gas reservoir of gas, fall at high velocity, at high speed in the clusters, the cold gas from the galaxy interacts with the hot gas, and this creates a gradient pressure, and this removes the gas from the galaxy. That's what you see here in red. So this is a nice example in the Virgo cluster, where you see the gas, an ionized tail of ram pressure stripped gas. And this is a mode to quench star formation and also to remove gas from the outskirts, which means that then the only stars that can form are those that are in the inner part, and this can also explain the fact that the galaxies look smaller. The other mode of, the other mechanisms are related to gravitation. So this can be either galaxy-galaxy interactions, including multiple flybys of galaxies one to the other, minor and major mergers, as you can see here. So major mergers completely destroys the morphology of a galaxy and rebuilds the angular momentum of the galaxies. And the other mode is gravitational interactions between galaxy and the cluster. And those mechanisms have an impact on the morphology and also on the kinematics. So let's try to make a kind of short story. So what happens when the universe is born? We think that, okay, after the Big Bang, there are small density fluctuation of the dark matter. And when the times goes, the cosmic times evolve, I mean, the dark matter will condense into walls and filaments and so on, and create the spider web, the web structure that we see here. So basically, we can think that galaxies start in kind of homogeneous density, low density regions, and then they fall into filaments, these dark matter filaments, along this, and in those filaments, they can form, they can aggregate to groups, and those groups continue their infall to the nodes of the filaments into clusters here. And we think today that there is a mechanism called preprocessing, where galaxies evolve small step by small steps as they go to denser and denser environments, which means that there is a probably the interaction between galaxies and the most and more massive dark matter halos creates the evolution of galaxies. So I'll go more into where we want to go. So we are interested in redshift around 1. So here is an example on the left of one field in a part of the cosmos area, the cosmos field, where we have when people have found a high density structure called the cosmos wall, where we have filaments, we have groups, and we have kind of cluster that at the encounter of the filaments. And redshift 1 is kind of a sweet spot to study the impact of environment, because at this redshift, the clusters are still assembling their mass, and the structure are starting to get virialized. And we are also right after the peak of star formation, which means that we expect to have many galaxies, star-forming galaxies, that still infall into the groups and clusters. And so this is the population that is supposed to evolve the most here. So yeah, that's why we are interested in that redshift range. And so I want to mention work. I think it's the only work before the magic sample. It was the only work that was done to study the impact of environment on galaxy kinematics. So it's a work done by Deborah that is here, and she did the nice work. So she used integral field, long-slit spectroscopy to observe the kinematics. So she extracted the kinematics as part of the work that we did together when she was in Marseille. It was not on this sample, but it was the methodology was there. And the idea then is to, once you have the velocity measured in the rotation curve parameters, you can draw the Tully-Fisher relation, which relates the magnitude of the galaxies or the mass, the stellar mass, with the rotation velocity, which is a proxy for the dynamical mass, including the dark matter. And so she made the comparison between one sample of galaxies mostly in field, low density environment, and a specific sample, dedicated sample that was observed around the dense clusters to really try to see if we see evolution of this Tully-Fisher relation. So the result she had was that there is no significant evolution in the Tully-Fisher relation, but on the other hand, other thing that is really interesting to study is the evolution of the angular momentum, because we expect that angular momentum is a very fundamental quantity, and then when galaxies evolve, they have to make evolve their angular momentum. And so she did the same kind of analysis with this and found, it's small, but still noticeable difference between galaxies in groups and galaxies in clusters, I would say in dense environments, and galaxies in the field. So, so we wanted to, when we started our project with Muse, this paper was not there. We was not even aware that you were working on that. And we had the same kind of idea of, so sorry for this being very small, it's not expected, but anyway. So we were wanted to do the same kind of analysis using integral field spectroscopy to have two-dimension information about the kinematics. And so we wanted to study the impact of environment on scalar relation, so redshift around 0.1, around 1, sorry. And so the scaling relation were the SFR mass relation, main sequence as I showed previously, the size mass to see if there is indeed contraction, and the Tilly-Fisher relation, and the follow relation, which is the relation about the angular momentum shown previously. And so we wanted to have a sample that tried to minimize the biases that can be made in such studies of relatively big samples. So when we go back to what was done at that time with integral field spectrograph, it was the time where KMOS was starting to be on the VLT. So KMOS being a multi-object integral field spectrograph in the infrared. And thanks to this new instrument, they were able to build sample of about 1,000 of galaxies. But there is one drawback with such a multi-object spectrograph is that you always need to do a pre-selection. So select which galaxies you want to observe as part of your sample so that you get some efficient observations. And doing that means that you need to have a good photometry, to have a good estimate of the photometric redshift, which means that you need to have, I mean, usually you are more focused on massive galaxies, massive star-forming galaxies. So there were also some surveys dedicated on clusters, but those surveys, the problem is that they are more focused on passive galaxies, which makes the thing a bit difficult because you don't have the whole population of galaxies in those kind of samples. And the other thing is that even if the samples are large, they were not specifically made to, I mean, built to tackle the environment issue. And if you took galaxies randomly, there is good chance that you are not on a high density region, and so that you don't sample the very high density where things may happen. So we wanted really to do something that is able to answer this question and tackle this specific issue. So we wanted to minimize the best and to go to low mass galaxies. We wanted also to have a good completion in our observations, so not miss too much galaxies in a given structure. And we also wanted to build samples in various environment that we can compare together in an homogeneous way with a similar methodology, so with similar observational setup and so on, to really minimize all these biases. And as a bonus, thanks to Muse, we thought that we would be able to be sensitive to the intragroup or intra-cluster medium. Even if I present it here, and when we did that at that time, we didn't think about that, but it was a byproduct. So let's describe now the survey. So this is the paper that was accepted this year. And so all I will present in this part comes from this paper. So this magic sample is a 70 hours Muse GTO survey. So I had the chance to work with this, to be in that team and to have this time. And so the idea was to target known dense structures in the cosmos field. So this is an image of the cosmos field, and you see all the small squares here are the fields that we observe with Muse. Most of the fields were observed at exposure times larger than 4 hours. We have 1 10-hour field here and 4 1-hour fields that we just observed 1 hour because they were a bit less interesting in terms of the galaxies we saw in first snapshot observations. And so we selected this cosmos field because it has a very extensive multi-band photometry. And we started from the Cosmos photometric catalogs, which enables us to get to do ACD fitting and to get fundamental properties of galaxies such as their mass and star formation rate. And just to say, we can think when we see that the small field of view of Muse is very small compared to Cosmos. But in fact, the field of view of Muse at redshift around 0.7 corresponds to about 500 per kiloparsec, which match very well the size of groups massive groups, let's say. And still, thanks to the good quality of the site, the spatial resolution is very high, and we have a resolution of 5 kiloparsecs in the galaxies themselves, which is very nice to study kinematics. And the spectral resolution is about 3000, which enables to have an accuracy on the measurement of velocities of the order of 10 to 20 kilometers per second, which is essential if we want to measure the properties of groups as the velocity dispersion, but also to study the kinematics within the galaxies. Okay, so the first thing we had to do was to determine the redshift from the spectrum. So for each entry we had in the photometric catalog, we extracted a spectrum, and from this spectrum we derived a redshift and a confidence flag associated to it. So I just go through a few examples. So the high confidence is where you have clearly the redshift is clear because you have many features, spectral features. So here you have, for instance, absorption lines that are very typical, that you have no doubt about what redshift it is. You have also case like here in the middle, maybe I should use the mouse here, where you have multiple emission lines that makes no doubt about the redshift. And then you have case like this one, where you have only one, you may have several features, but they are at low signal to noise ratio. So we put here a confidence 2, even if we have not too much doubts. And here we put confidence 1 when we have a tentative redshift. In that case, for instance, we think that we have the oxygen 2 doublet, but it's also at the same level of the noise, so it's not completely clear. And so the good thing here with the Muse, with the strategy of observation with a large monolithic IFU, integral field spectrograph, is that we have here the square corresponds to the galaxies that we expected in the group, but we also have at the same time, we can build a sample of galaxies that are in the foreground and in the background because we have redshift for all galaxies in the field of view. And doing that, this allows us to build the redshift distribution here. And so what we see is that we have multiple class I divided that in multiple class. So on the one hand, we have the stars, okay, that we discard for galaxy analysis, of course. We have nearby galaxies and oxygen 2 emitters between redshift 0 and 1.5. Then you have the redshift desert because you don't have much spectral signature in the optical. And then after redshift 3, you have Lyman alpha that enters into the spectral range, and its shape is quite characteristic at the resolution of Muse. It's enough to be able to know that it's Lyman alpha. And so we see here that we have a peak in the distribution around redshift 0.7, and this is due to the fact that this is the redshift where we targeted the most of the structures. So the first thing we did, was it useful to do it in terms of redshift? And if we compare with the previous spectroscopic campaigns that were quite numerous for the Cosmos field, and we look just within the area covered by the Muse field of view, we see that we have an increase by a factor of 5 of the number of new secure spectroscopic redshifts. And when we look at the distribution here in terms of apparent magnitude and redshift, we see that most of the new objects are objects that are faint magnitudes, that are magnitudes below 21.5 typically. And it's just because it's just the selection effect that previously you just target the galaxies for which you think you will get something because they are bright enough. And so that's where we have the better gain with Muse. And here also this makes that the gain is high also at high redshift because most of the galaxies are faint, so they were not targeted previously. Yeah, this is, I think, a great result. So we also wanted to check that because, okay, we have galaxies at low mass in principle, but are we complete for those galaxies? What's the completion rate? So we look at the completeness, and if we look globally just for oxygen 2 emitters, so between redshift 0.2 to 1.5, if we look in this range, we see that we have a completion of 80% up to magnitude almost 26, which is quite good. And if we look locally, that means in each beams here that are drawn in this figure, that locally we have a completion better than 50% for magnitudes up to 25.5, which is very good compared. I mean, that means that the new galaxies that we get with our survey have still a good completeness, even if of course, we miss some, and especially we probably miss galaxies that are not star forming, because for those galaxies, mostly we were using the emission lines. So we drive that in terms of the mass, but I will not spend too much time on that. So then,
sorry, Benoît, yeah. I probably should know this, but so you use the photometric positions as a prior for redshift measurements?
No, redshift measurements, spectroscopic, are done independently from the spectroscopic.
But you extract the Muse cube at the
position.
position. And
Yeah.
do you do a search for objects that are not in the Cosmos 2020 photometric catalog?
Yeah, so I didn't mention that, but we did that. So there are two things. For the galaxies for which there was an entry in the photometric catalog, sometimes we find two redshifts because clearly there are two galaxies on top of the other. So in that case, we identified the two and could sometimes put two redshifts. And we also run, but it was not done systematically on all the fields, but we also did a search for objects without any knowledge, I mean, without any a priori, just looking in the cubes. There are tools to do that, but you can also do it manually. And we found hundreds of galaxies this way. But the problem with those is that we cannot include them in our analysis because we don't have the photometry measurement. So it's a bit more difficult. So I go back to the next. So the goal is to study environment. So we need to quantify environment and to check if galaxies are in groups, clusters, or whatever. So we do the very basic thing to start with, is to use friends of friend algorithms. So the idea here is to say if you have two galaxies that have parameters that make you think that they are gravitationally bound, and one of those has other galaxies that could be part of the same group, you say everyone is together, everyone is in the same structure. So to do that, typically you take an angular separation between two members. So I decided to use proper separation, proper distance separations so that it's physical. And same in terms of redshift. So I converted redshift into a velocity separation because it also gives you if galaxies can be gravitationally bound in terms of velocities. And so using those parameters, you can determine if galaxies, you can find groups. And this is an example here where in this field, I showed two groups that were found. So one is the one that was targeted, the one in red. But we found, looking at the data, that there was in fact another group. And when you look at the redshift separation, so we find that using the friend-of-friend algorithm. When you look at the redshift separation, it's clear that the two cannot be gravitationally bound. They are two different groups, even if the redshift is close, but they are at two redshifts. So this is very powerful to find groups. And so we also wanted to determine more local environment estimates. So to do that, I really want to thank Brian that helped me in that work. That he did the work on our fields. So using the Voronoi Monte Carlo method that he has developed and used in his papers. And so basically this method is using all the spectroscopic redshift that were known from the Z-Cosmos catalogs. And also on top of that, it uses the photometric redshift of the galaxies for which we don't have any spectroscopic redshift, and enables by iteration to find probabilistic density or over density. So the interest here is that with this method, you have an homogeneous sampling because the dataset is very homogeneous over the whole Cosmos field. And you also are able to provide a density estimate, local density estimates to any galaxies, regardless if they are in groups, clusters, or in the field. So this is very nice. So just as a comparison here, we did also simple Voronoi tessellation measurement using the Muse redshift and only spectroscopic redshift. So we see that the agreement is very good and it's the same field. It's very good. The drawback of this method is that we have edge effects because the density of redshift, as I shown previously, is much lower at the outskirt of the Muse field of view. So you cannot really know what's the real density at the edge. The interest is that you get a higher spatial resolution, but the edge effects, I think, is a major limitation. So here are the properties of the groups that we found. So I show here the virial mass as a function of the group richness. And so the virial mass is computed from the velocity dispersion of the galaxies in a group. So what you see here is that the galaxies are color-coded, the groups are color-coded in redshift, and the square, when it's the outline in the square means that these are the objects that were targeted. So we see that the most massive groups that we find in MAGIC are those that we targeted previously, but we see that we have, thanks to the fact that we have galaxies in the foreground and background, we found many other groups that are smaller mass and lower richness, but clearly we found many groups in the end. And so in the end, we found 76 pairs of groups, 67 groups where we targeted 14 at the start, with 19 with more than 10 members. And most of the groups are at intermediate redshift. So this just shows the statistics of the number of galaxies in the group. So we see that many galaxies are in pairs, but we have a good statistics for various-lessness, which is important, the interesting thing. Okay, so first thing to do when you have such a sample is to check that the groups you have are meaningful. So to check that, you have to check that the red sequence is as expected. So we define the red sequence using the color diagram, as shown in any of this figure on the bottom. From that, we separate quiescent galaxy from star forming. And if we put that in the SFR stellar mass plot, we really have the star forming galaxies where we expect them on the main sequence, and the quiescent galaxies below a given threshold of star formations, which is exactly what we expected. So that's just perfect. And the interesting thing here is that when we look the evolution of the main sequence of the fraction of quiescent galaxy, when you increase the density, the over density, you see that you go from a fraction of 5% where you are in very low density to about 50% when you are in high density environment. And this is really a continuous evolution of the fraction of red sequence galaxies when you increase the density, which means that really what the measurements we have about density are just what as expected. So we can also look this in terms of phase space diagram. So what we call phase space diagram is a diagram where you have, on the one hand, you have the velocity within the structure compared to the velocity dispersion, and on the other axis you have the separation between the galaxy and the central on the center of the group, divided by the virial size of the group. And this can be encapsulated into this eta parameter. This is the product of those two. And here in this plot, you have the lines here are isocontours. And so this creates some separation between different kinds of galaxies that are related to a global environment, but also to the time spent in groups. So galaxies that are with the largest eta parameter, so in this region here, are galaxies that are infalling. So it's their first infall on the clusters. And we see that the fraction of quiescent galaxy that is color-coded here is basically very low. But when you go to the region in the middle here, what we call the backsplash galaxies means that they already have first pass to the pericenter. The fraction increases, and when you go to the smallest values of the eta parameter, you have galaxies that were located very early, so that are close to the center or close in velocity to the velocity, that have small velocity with respect to the velocity dispersion. You have it's where you have the highest fraction of quiescent galaxies. So, which means that the red fraction also increases as the time spent within the structures. So here just to show the properties of the galaxies in the sample. So here we look the histograms of the stellar mass as a function of environment. So the various colors corresponds to various environments. Sorry, I forgot to put the environment, but black is the highest environment and blue is the low environment. And what we see clearly is that as you go to dense environment, you have more massive galaxies. And this could be due to the main sequence, so to the red sequence. So if we excluded it, the effect is a bit less, but still you have the same trend, meaning that when you go to higher density, you get a higher fraction of massive galaxies. And you have fewer mass galaxies in the densest environment, so which could mean that small galaxies are merged to higher mass galaxies as the density increase, which could be a proof of preprocessing, meaning that when galaxies evolve along the filaments, the small galaxies just don't exist anymore because they have merged or something like that. So this also shows one difficulty one may have when trying to study the evolution of galaxies as a function of environment, because if you want to draw two samples, one in high density, one in low density, you don't have the same mass distribution, which means that you don't compare the same kind of galaxies. And this is one limitation, we try to work on that as much as possible doing the analysis that I will present here. So this analysis really on the core of the
Can I ask a question on the previous slide?
Sure.
So I noticed not only is the distribution of the stellar mass distribution of galaxies in groups shifted towards higher mass, but that's also true of star-forming galaxies in the groups.
Sorry, just to manage to get back. So can you just repeat it?
Yeah, so the stellar mass distribution
Yeah.
of galaxies inhabiting the groups versus the field
Yeah.
is shifted to higher masses.
Yeah.
But that also persists when you remove the red sequence.
Yeah.
And so I'm wondering the galaxies that are high mass, that are star forming, that are presumably highly star forming or potentially on their way to quiescence, where do those show up in the groups?
So which galaxies? Those that are massive but still star forming?
Correct. Yeah.
You mean in terms of position or?
Phase space diagram. Yeah.
I don't know. I haven't looked at that in detail. And there are not that much galaxies that are very massive and very star forming. But yeah, that's interesting. We should look at that.
Do you see a bimodality in terms of star formation for those galaxies? So some are on their way to quiescence and others are still...
Not really. We don't see really those on transition. It's not something. That was done that I don't show here is that we looked at the morphology also. So the bulge disk ratio for the galaxy. What we see is that most of the quiescent galaxies are bulge dominated as expected. And there is really a dichotomy. The star forming are not bulge dominated and the quiescent are bulge dominated, which means that the transition seems to be very fast, I would say. But yeah, I cannot really expand more because I don't have it completely clear. About the location of those galaxies.
Okay, thanks.
Okay, so the next part is about the impact of environment on scaling relations. So this is the work that was mostly done by the PhD students that I had the chance to have working on this project. And so just a few words about methodology. So the idea was really to extract the first idea was really to focus on kinematics because that's where anti-wide-field spectrographs are powerful, the most powerful. And so we wanted to extract morphokinematics to morphology and kinematical information. So this is just to show that for any of the galaxies of our sample, we had HST data on which we perform a bulge disk decomposition. And this is very important to us because doing that, it allows us to have constraints on the position of the galaxies, on the disk size, and also on the projection parameters, especially the inclination of the disk. Okay, and for the kinematics, so we extract kinematics from emission lines. So it is mostly for emission line galaxies that is done, where you just measure velocity from Doppler effect. And so you can draw a velocity field as shown here. And the idea is to model it by taking into account the projection effects of the velocity along the line of sight. So you need to have the inclination and projection parameter, and also the beam smearing, because still if the spatial resolution is about 5 kiloparsecs on the galaxy, which is good, but it's still low compared to the size of galaxy. So it's really important to get rid of the beam smearing effect. So we have a forward modeling approach here with many parameters, and to help these models, we fix some parameters from the morphology, so especially the center and the inclination of the galaxy. And so once we have that, okay, so this is just quickly speaking about what was extracted. We did a huge work on the sample selection because we wanted to avoid most of the biases that can be seen. And so we decided to remove many galaxies that could have been included otherwise. But the idea here is that we put a cut here on the size of the galaxy. We want galaxies to be spatially resolved. So this parameter can look a bit complex, but the idea, in fact, is to count the number of spatial resolution elements you have in 2D on your map. So basically, this is the area, a proxy on the area of the galaxy, taking into account the projection parameters. And on the other hand, we also want to have a good signal-to-noise ratio because we don't want to be biased in our measurement by galaxies that have very low signal-to-noise ratio, for which we think we have a good measurement, but in fact we don't. So that's where we end up with those galaxies here, the black points that we show here. And we also remove low inclination system, because when you have gas that is rotating, which what you expect in star-forming galaxies, so you have to deproject, and the deprojection is proportional to the cosine of the inclination. And so if you go to low inclination, the deprojection is very high, which means that the uncertainty you have on the real amplitude of your velocity is large. And this is a problem for Tully-Fisher relation studies. So we just wanted to do a safe t-check here. So we did that on a preliminary sample of 67 galaxies in 8 groups. And here is the Tully-Fisher relation. So we have the stellar mass as a function of the velocity. And the selection retains all the galaxies that are circled in black. And what we see is that the galaxies that are removed from the selection almost removes all the outliers that we had here. And those outliers, we can see that they have a low velocity over sigma ratio, which usually this ratio is used as a proxy of what's the support, the dynamical support of the galaxy. But this means, in fact, that for those galaxies, it could be that this ratio is low just because we're not able to measure correctly the velocity due to low signal to noise ratio, for instance, or due to low size because you're not resolving your galaxy. So this was a first result, because what is done very often in this kind of studies by all the other authors is that they take everything and in the end they say, okay, I have outliers, so I remove them. Or I have the galaxies with a low V over sigma, so I remove them, but there is no real justification apart that they are strange. This kind of galaxies, outliers, in the local universe, you just don't see them. They don't exist. So that's probably something that more methodologically related. So, and that was the idea of this selection, this very restrictive selection function. So, as I told previously, when you want to compare environment, you need to be able to compare samples that are comparable. That means that they have the same kind of stellar mass distribution, which will be the first parameter. So, if we look at the stellar mass distribution before doing a mass cut, clearly you are biased to high mass in high density environment. So we decided to put, for the final analysis, we need to put a cut in stellar mass to 10.5 in log stellar mass, which is usually the threshold that is used for selection in other samples. So that's really something that's interesting. So during his PhD, Wilfried looked at many scaling relations, especially the size-mass relation here, where he could find an offset in the size. So size are 50% smaller on average at fixed stellar mass in high-density environments. High density being the red dots here. So which means that we see baryon contraction in the magic sample, similarly to the other result that were shown previously, but like here, everything is done in a very homogeneous sample, so that's nice. He looked the same kind of relation for the main sequence, and here again, he found what was expected, that we have a reduction by a factor of about 1.5 in the star formation rate at a fixed stellar mass in dense environments. And then now I go to the Tully-Fisher relation. So just want to emphasize on that. So we had the first results, and it was the work of Valentina. It was on the preliminary study of a subsample of only 77 galaxies. So the sample was not assembled completely yet. And we here compared these galaxies to other samples obtained either from CHEMOS, integral field spectrograph, but also to the work done by Deborah from long spectroscopy. And we found, in this study, we found offsets. And so we had two main explanations for that. The first was saying that, okay, in fact, what happens is that due to quenching, the velocity, so in that case, we say that the velocity traces the dark matter halo mass. But since you quench the star formation, that means that galaxies in dense environments cannot form many stars. Okay, so compared to galaxies in field, you have a less stellar mass. So this could explain that if you have at a fixed halo mass. Okay, so this, if you assume a decrease of 0.3x of the star formation rate between groups and the field, this this means that the quenching time scale is about 1 to 3 gigahertz. So this was the first way you can interpret that. The other way is that, in fact, the velocity traces the mass within the radius in which we measure the velocity, which means basically, I mean, first approximation is proportional to the product between the radius at which the velocity is measured times the velocity square. And in that case, if you measure a difference in velocity, and you assume that you have had a contraction of the baryons, you can explain part of the velocity increase, sorry, because if you put the same mass in a smaller radius, you have to rotate faster. So this can explain part of the offset. So in this study, we cannot really say which was which, and maybe we say that maybe there is a combination of both effects. And the latest idea was that maybe there is methodological biases because we compare samples that have been observed with different instruments, sample selection is completely different, and so on. So Wilfried, during his PhD, he did this work of using only MAGIC, so galaxies in groups and those that are not in groups, to compare to study the impact of environment. And what he found is that, in fact, there is no I mean, it was the first self-consistent analysis of the Tillich relation as a function of environment, and clearly we saw no effect, no clear effect of the environment as the result you had with from your work, Deborah. So, which seems to indicate that there when you compare the samples that are very different, there can be methodological biases that are very, very large. So next, he derived the angular momentum. So we wanted to do a bit something fancy to change from what's done usually, because we have this information. The angular momentum here can be expressed as the integral over the area of the galaxy of the radius times the surface density times the velocity. And then you have a normalization factor. We didn't really care. But then the radius, you know it because you have the geometrical parameters, projection parameters of your galaxy that are known. The stellar mass density is known it can be inferred from imaging, and then the velocity is known from the kinematic modeling that we have. So using that, we did this measurement, and we studied the impact of environment on the correlation. Well, it's really super late already. So we found a depletion of angular momentum in dense environments that is 2 sigma significant. So and we found something not really expected, but that's if you go to massive galaxies, you see that they are below the correlation that is inferred from the low mass galaxies. Okay, so he saw kind of impact due to the, what he did is that for galaxies in groups, he looked at this eta parameter that quantifies the time spent in the structures, and what he found is that typically, there are more galaxies below the relations that are with the low eta parameters, which means that they have spent a long time in the structures. But still, to make a very nice comparison, we lack massive galaxies, field galaxies, to discriminate between environment and mass-driven effects. I will go further on that because I want to show you other things. So these are the cool stuff we found serendipitously in the data sets. So we found several nebula. So this was the first that we found, and that we make the first publication on the MAGIC data set was that one. I mean, I was supposed to work on the sample at that time. It was 6 years ago. And when we found that, I said, no, you have to do this paper. I said, okay, but then I will never do my paper. But sorry, now it's done, so I can present things more relaxed. Yeah. So this was in the second most massive groups that we found this gigantic Jonas gas structure. And when we looked at the properties, so several lines were present, so we could try to understand what are the ionization, the source of ionization. And what we found is that depending on the region, we have here an AGN, and this region that is this color here is clearly ionized by the AGN, whereas on this region it's more shocks and I would say that just usual ionization by stars. And so the question is where these gas come from. So it seems that here in that direction, so we have the kinematics, that we were able to derive the kinematics of all these extended nebula. And around the AGN, we seem to see some tidal arms that could be interaction, but on the orthogonal direction to the major axis, we have a kind of jet-like structure that could be gas expelled from the AGN. And here is probably, I mean, it's completely a mess, this region, but it's probably interaction between galaxies with tidal arms. There is maybe also some pressure stripping of galaxies that enters into this very dense region or whatever. But it's really interesting because around the most massive galaxy of the group, we seem to see here a rotation, a velocity field of rotation. And when you look the stellar kinematics that we were able to derive here, we see that the directions are orthogonal, which could mean that there has been gas that has been expelled in the medium, and this gas is resettling into a disk around the most massive galaxies, but with a different orientation, which is kind of cool to see that because it's things that we see in the local universe, that some galaxies have several disks. So that's it. The other interesting thing we had was...
Sorry, I know you're going super quick, but is there a hot IgM here that is measured from Chandra?
So there is X-ray emission. It's not completely clear to me because I'm not an expert on that. It's not completely clear to me if it's related to the AGN or to the group and how to discriminate between the two.
But typically with Chandra, you can remove the point source and you can...
With Chandra, I don't know. With XMM, clearly we have it. And this is part of the groups that are identified with the X-ray counterparts. So it has, but I'm not completely sure it's there at this location. Because it doesn't seem to be the central region of the group. This group, I don't have it to show, but it's kind of filamentary. It's completely elongated with really this region here with more galaxies, more dense, but it's like kind of a small filament. So maybe it's, there is probably, I would guess that if there is X-ray emission, it comes from here.
Okay, and the most massive galaxy, most stellar massive galaxy is the one.
Is
there
this
right in the
one?
middle?
Yeah, is the one on the center.
Okay.
Yeah.
Thanks.
Okay, so let's move on. So we also found the first RAM pressure stripping event at recife 0.7. So I will just go very quick. But here we have two galaxies for which we find oxygen 2 tails, so ionized gas in oxygen 2. So here is the allocation with respect to the center of the group. So this is the X-ray emission for that case. So X-ray is very clear on that one. This is more than a group; it's more a cluster. I mean, it's very massive, and there is no clear stellar counterpart, which is an indication that this is RAM pressure stripping. And the other indication that it's RAM pressure stripping is because the gas seems to be decelerated in the tail, which is what you expect if you have a galaxy infalling. The gas is stripped, so it's decelerated necessarily. So this was very nice. And to see two of them was very surprising because their velocity separation is quite large. So one of the ideas was that maybe those two galaxies are inside a filament or in a wall that is and they are infalling in the same plane onto the galaxy, but they are not very relative one to the other. It's really by chance that they are very close one to the other. But their location in the cluster means that it's probably the first time they pass through the cluster. So in the survey paper, I also wanted to highlight other nebula that we found, mostly because I don't think I will have ever the time to make a deep publication about those. And I'm really happy if people is aware that there are things that are cool here and that they want to go further on those. So anyone could, of course, use this data. So we have found this structure here that could be stripped gas with some gas falling back to one massive galaxy here in the central region. But it would be more gas stripped from this one, or it could be an interaction between those two galaxies that creates a bridge. Not completely clear. We have only oxygen 2 on that one. And we have also this one that is kind of nice, where we have a quasar here. It's not very high mass quasar, but still we have an extended nebula that is ionized by the quasar itself, which means that either the quasar is illuminated gas that is from the CGM that is around, or that this galaxy during its infall on the group is losing gas. And some studies claim that when you have RAM pressure stripping, this can this could induce nuclear activity, and this could be the reason then for the quasar itself. Okay, so I can go back to my conclusions. So I will be quite quick, but here is just a summary of what I've already said. So we are happy because in the end, our sample enables us to go to low mass with a good completeness, with a wide diversity of environments. We have clear weight sequence that is, as expected, continuously growing from when under environment gets denser. And here we were able to study the impact of environment on scaling relation, and we see noticeable evolution of the size mass, SFR, and also for relation, but no noticeable evolution of the Tully-Fisher relation. So this favors a scenario in which environment impacts, in fact, the morphology and the rotation curve shape to be able to do all that. If you want more, I have slides that I just kept previously to be on time. So the survey was also the occasion to present a new selection and new methodologies to avoid methodological biases. And the data set is very rich with many unexpected stuff. I show some of them, but there are more if anyone looks in the data cubes with the RAM pressure stripping, AGN activity, shocks, galaxy interactions, and so on. And so I'm quite happy because, I mean, I want science to be spread and to be shared. And so we have made the catalogs public and also the data cubes. Last time I was here, I was telling you that I had troubles with phase 3 of FISO, and I finally managed last week to get the data published on the phase 3, so which means anyone can go and pick up the cubes that we reduced the best as we could. So what next? So next, I think we may want to better understand the evolution of angular momentum. So this can be done with the magic sample itself by not looking at the environment, but more looking what's happened when you include both high mass, low mass, and so on, and see if you have link with bulges and so on. So this is a work that Wilfried is supposed to do at some time. And also you can study the impact of environment on quiescent galaxy from the stellar kinematics. So this is just to show that stellar kinematics are within the reach of MUSE with the deep fields such as those we have. So there was a pioneer study of Adrien Guéroux. We studied 17 galaxies, star-forming galaxies. He studied their stellar kinematics on deep fields. And just recently, I think it was last week, we have Constanza, that is a student in Germany, that's published first analysis of about 100 galaxies with stellar kinematics, so significant increase in terms of sample. And she tried to study the impact of environment on those, but she was still using data that are not specifically dedicated to dense environment. And so there was not enough environment diversity and not enough galaxies in very dense environment to find anything. So the next step would really be to use the magic samples, because we have many galaxies, more than 80 galaxies for which we expect to be able to derive stellar kinematics and that are very massive, more to the 10 with a strong rate sequence. And she also now work on the integrated stellar properties, stellar kinematics properties of the galaxies using magic, but also other surveys. So yeah, we can also think about doing statistical analysis of extended nebula, noticeably to constrain the rate of quenching processes at intermediate redshift. And we can also want to improve the analysis with more fields. So here I just show an example. So these are the fields that have already been observed and published. There are many galaxies there, but there is a new project. This is the latest MUSE GTO project. So the observations are over now, but it was observation over Hubble frontier fields. So we have very deep HST images on those. And so this is the wedding case observing strategy that I showed. Maybe it's not very useful, but the idea is that it will cover a larger volumes because these are mosaics of 2 by 2 arc minutes, and you have chance to increase the diversity of environment and to get more galaxies also to compare at high mass, because if you increase the volume, you increase the number of galaxies in low density environments with high mass. Okay, so at longer term, yeah, we want to have to increase the statistics and to have larger IFUs to map cosmic web at intermediate redshift, because here we look at groups, but we think that preprocessing starts in cosmic filaments. So it could be interesting also to look at that. And to do that, we need a larger field of view. So we have blue muse, but it's not completely significant, the increase of the field of view. There is also this WST project. So there is a white paper that has been published recently. The idea of the WST is to have it's a MOS plus a monolithic IFU in the middle, which could be patrolling a field of view of 9 by 9 arc minutes doing mosaicing. And 9 by 9 start to be quite large to do interesting stuff because you increase by factor 9 the size around the clusters, around the groups, and so you start to have filaments and these kind of things. So, but yeah, in the meantime, the larger IFU already exists, in fact, and it's something that I think some people don't think too much about it. So since this is the IFU we have at CFHT, I just want to mention this land acknowledgements here because we are using the mountain here that is of significant importance for people here. And so this instrument, CITEL, is an imaging Fourier transform spectrograph. So it's not really the usual IFU with a slicer with fibers and so on. But the idea of such instruments is that you have one detector that is completely used for imaging. And with a good sampling, with the spatial resolution is nice. And the field of view then is very large. It's even larger than what we expect with WST. It's 11 arc minutes square. So it's 100 times larger in terms of area compared to MUSE. And it has a tunable spectral resolution up to 15,000, which is very large compared to MUSE as well. And the spectral range is large. The drawback here is that you have to split your wavelength range to have, I mean, you have to use filters to observe a small fraction of the wavelength range. But doing that, you can do things because if you have a narrowband filter that the widths match the velocity dispersion of the groups you want to observe, then you can have a very efficient instrument to look, for instance, here a cluster with maybe an infalling group or these kind of things. And I just want to mention that because we commissioned very recently a new filter that is the narrowest that we have. The idea of this filter was that with such instrument, if you narrow down the spectral range, you decrease the noise that you get in your data, and so you increase the sensitivity. And one of the goals was to study this galaxy here, where you have one pressure repeat. So this is the one I showed in the introduction in Virgo, where you have this very nice filaments that were observed with megacam. And we were able to get the first observation with CITEL. I just managed to reduce that last week as well. And so we are able here, this is the original image, the fancy image, I would say, from megacam. And here, this is the lendization maps we get with CITEL. So we have the galaxy clearly here with some filaments here, but we also managed to get all these filaments that are here, the Ramprecious stripping tail. We have those here as well. And we were able from that to get a velocity map, which is really important if you want to understand, to constrain modeling of front pressure stripping in dense environments. So that's for it. Thank you for your attention and sorry to be that long.
Any questions for Benoît, either in the room or online? Thank you for the very, very comprehensive talk.
Yeah. Thank you. I hope it was.
Are you looking to go to a higher redshift with CITEL?
With CITEL, I think we are limited because we are still on the 4 meter, so it's a bit difficult. So the idea would be to go up to intermediate redshift 0.5, maybe 0.7 would be probably the maximum. The other thing is that if you have a source, you need to have a filter that matches exactly the redshift of your source. So right now we have a filter, and so we have to find source that fits within it. So it's not that easy, but I have some.
What's the wavelength range of the filter?
It's 10 nanometers. So the filter we bought was really done to do multiple science. So the idea was to be able to do local universe. So we focus it around H alpha, which means it's around 6,500 angstroms. But that means that in this range, you can get the oxygen 3 line at redshift 0.3, the oxygen 2 lines at 0.7. So we just need to find the source that goes in. So I have some already some candidates to do that from the Vestige survey, which was targeting Virgo, because there is deep imaging, and also this HFA image, this line imaging from the H-alpha filter from Megacam, which allows you to see if you have line emitters. And so if you target those structures, we expect to have things. So I have one field that I observed in the commissioning, but I haven't had the time to check that I have detections there.
Any other questions?
I guess that was just a curiosity.
Yeah.
Is there any plan for the Lyman alpha emitters in Magic?
Not yet. I mean, we have them, but
How many people are there? Seems like
let me check.
hundreds.
I think it's in the paper. I have the paper here. Yeah, the table is here. We have Lyman alpha, where we have 150 with secure chip. And those are only those that were, it includes 50. In fact, if we did this work of doing systematically a blind search, we would find, we would double this number maybe, or at least have it 200. Here in this table, I show in parentheses the numbers of galaxies that were found blindly, but it was done only on less than half the sample. So you double at least these numbers that are here. So it will do, yeah, we will have 250, I guess. But even using only those ones, you can do lots of stuff.
Seems like a good project.
Yeah, sure. We have no one working on that because we don't have enough manpower to do that. But yeah, there are many things that can be done. The data set is very great.
Yeah.
It's fantastic.
Yeah, it turns out there's a lot of protoclusters in the Cosmos field, and it would be interesting potentially to cross-correlate the protocluster catalog with the Lyman alpha catalog.
Yeah, sure.
Perhaps we can discuss that at some point.
Yeah, completely, because I've done the work also of running the friend-of-friend algorithm on the Lyman alpha emitters. So I already know where I would expect maybe some over density of Lyman alpha emitters.
And we have a VMC catalog for all the detections.
Yeah, we
of
could
Redshift
cross that. Yeah,
maybe after the talk.
Yeah. But then we need to by chance be on the right position.
Right,
But maybe you have something and we have something a group where you have a protocol. Maybe we have a proto group.
Yeah,
so maybe it's
they're
interesting.
crazy and sparse and all over the place. They're huge on the sky too. So yeah. Okay, if there are no other questions, let's thank Benoît again. And just a reminder, he's up in Waimea all the time, so go visit, say hi, give a talk.
Yeah, thank you. Cool. Done.
Thanks, Benoît.
Yeah.
That was great. There was so much stuff.
Yeah, there's too much.
No,
I don't know.